This is the story of a blue pigment unsurpassed in quality, a story of tireless effort and painstaking research, and a triumph of British chemistry. The discovery was indeed a major event in chemistry, because it not only gave us this fine pigment, which today is used in a multitude of ways, but it also revealed an entirely new type of chemical compound, the phthalocyanines, the importance of which can hardly be overestimated. The development of this blue is in fact a first-class yet typical example of the teamwork which today exists between all branches of chemistry, pure and applied, industrial and academic. Here there is no conflict of interest, but a true unity of purpose. This starts in Scotland. The year is 1928. And the place Grangemouth at the Scottish Dyes Works of Industries. Very many products were made in these works, both dyestuffs and intermediate compounds for use in the manufacture of dyestuffs. And at this time, the users of one of these intermediates, phthalimide, complained that certain preparations of it were contaminated with a dark-colored impurity. Now, the phthalimide had been satisfactory up to this time, and the first thing to do was to get a sample in order to investigate the complaint. This was fortunately easily done, as the impurity was concentrated in cavities as well as being distributed throughout the mess, and a sample could easily be scraped out, though of course still mixed with a considerable amount of phthalimide. Investigation of this sample would enable two things to be done: to find out how to remove the impurity from the spoilt material, and to find out how to prevent a repetition of the trouble. In the laboratory, the chemist investigating these problems found that the first was a comparatively simple matter to solve. He treated the mixture of impurity and phthalimide with boiling water, and by means of this very simple operation was able to effect a separation. The phthalimide dissolved, but the impurity remained insoluble and could be easily removed by filtration. This simple process not only solved the problem of how to purify the phthalimide, but immediately gave the chemist a sample of the impurity for investigation of the second problem, how to prevent a recurrence of the trouble. Now, obviously, before any steps could be taken in such a case, something had to be known about the nature of the impurity. Tests were necessary. In the first place, test tube experiments with some of the more usual chemical reagents would reveal whether or not the substance could be placed in one of the known classes of organic compounds. Almost at once it became apparent that here was something possessing novel properties, and it appeared possible that a new type of organic substance had been discovered. The dark impurity was extremely resistant to heat and to most reagents, and these properties immediately suggested that it might have some use in color manufacture. The question now was, how could this dark-colored product have arisen? Now, phthalimide is made from phthalic anhydride and ammonia, and in its manufacture in the works in an enameled iron vessel, there are only a limited number of combinations which could have given rise to the new substance. The components possible are phthalic anhydride, ammonia, any chips in the enamel which would leave small areas of exposed iron, or the enamel itself, and the impurity must have arisen from these in some way. Experiments were made to test this reasoning. In the first place, cuprous chloride was added to molten phthalo-nitrile. A vigorous reaction took place with the formation of a colored product. Another experiment was tried in which stannous chloride was used in place of the cuprous chloride. Here too a reaction took place, and in this instance with even more violence. Again a colored product was formed. Similar experiment was carried out with orthocyanobenzamide, to which magnesium turnings were added. Another deep coloration was obtained. These results confirmed the forecasts made and were the first step towards deducing the constitution of the new product, which in view of their mode of formation and general blueness in character were named phthalocyanines. In the meantime, in the laboratories of the Royal College of Science, work on the constitution of the phthalocyanines was proceeding apace. An essential to progress was a highly purified sample in order that an accurate analysis could be made. Working with magnesium phthalo, of sublimation was utilized. By heating in a tube which had been evacuated to a pressure of 1/10 of a millimeter of mercury, the product was found to sublime and collect on the upper parts of the tube in a very pure form which could be scraped. Again, by making use of the limited solubility of the product in some high boiling solvent such as chloro-naphthalene, and by continuous extraction in a form of Soxhlet apparatus, a pure sample of magnesium phthalocyanine could be obtained. The small quantities of pure product yielded by these methods enabled an accurate analysis to be made by microcombustion. In such an analysis, by using a microbalance, about 5 milligrams of the product is weighed in a small weighing boat, which is then transferred to the combustion tube. It is pushed home into position and the tube is tightly sealed. Dry purified oxygen, followed later by air, is passed through the tube, which is heated either electrically or by gas. At the high temperature reached, the product decomposes. The carbon forms carbon dioxide and the hydrogen forms water, which are trapped in absorption tubes and weighed. The nitrogen is determined separately, and from the results the empirical formula of the product can be calculated. The next stage in determining the constitution was to find the molecular weight. This was done by the boiling point method, in which the elevation of the temperature of boiling of the solvent resulting from the presence of a known amount of the product enables a calculation of the molecular weight to be made. Having determined this and knowing the empirical formula, and also knowing that the molecule contained an isoindole skeleton, a possible structure was deduced. The only reasonable way in which these 4 units and the magnesium could combine is like this. But this is not symmetrical, and in view of the quinonoid structure of one of the corners, could take any one of 4 forms. The properties suggested, however, that these 4 forms were in a state of resonance, making in effect a completely symmetrical molecule, which can be demonstrated in this manner. Such a structure can be represented in static form by means of a ball model, where the different balls represent the various atoms, and this structure, which enabled the shape of a molecule to be seen, and which had been deduced by purely chemical means, was fully confirmed later when the X-ray contour diagram of phthalocyanine was determined. But here too, when this was tried with copper phthalocyanine, and the product tested, there was still no significant improvement. There was, however, another way in which it might be possible to solve this problem. When a product is dissolved in a solvent and then suddenly precipitated from the solution, it frequently happens that such a precipitate is in the form of very finely divided particles. It was already known that copper phthalocyanine could be dissolved in concentrated sulfuric acid, and it was hoped that by making such a solution and then precipitating the compound from this solution by sudden dilution by pouring into water, a product of the right physical form might be obtained, although of course such a procedure would be more complicated than the more direct methods so far tried. An experiment was therefore made to test this idea. It was found by trial that the best results were obtained by pouring the sulfuric acid solution into nearly boiling water, and when this was done, a brilliant blue was produced. All the phthalocyanine products made up to this time had been dull or dark in color, but here for the first time was created a really brilliant blue. From the liquor, the blue pigment could easily be separated by filtration, but it yet remained to test the product. Would this new form show the desired improvement in properties? Only a careful and complete examination could show. Now, although the research chemist is an expert in his own particular sphere of activities, he cannot at the same time be a specialist thoroughly acquainted with all the varied needs and problems of the pigment-consuming industries. It is a cardinal point in all work of this sort that the products should always be tested by the specialist technicians, each of whom is an expert in his own particular sphere. Such workers are the colleagues of the research chemist, and their work is complementary to his. Thus, when the product had been isolated and dried by the usual methods, a sample of it was submitted for examination once again in the technical laboratories.